Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in today's session of rotational motion chapter, we are going to deal with the lecture number 4. So we are going to continue our previous topic, that is moment of inertia. So we have already discussed about the moment of inertia, right? So what is the moment of inertia for the uniform rod and for the circular ring? So we already have the formulas from the previous session. So in today's session, so again we'll see the moment of inertia for the continuous mass distributions like rectangular lamina and triangular lamina, cylinder, solid cylinder, hollow cylinder, and then solid sphere, hollow sphere, and then cone. So all these things, moments of inertia, we are going to discuss. And parallel axis theorem we also discussed in the last session. So and we'll discuss perpendicular axis theorem in today's session. Okay, chalo. So and we'll solve n number of numericals. So I just need your attention for the next 1 hour, guys. So just be with me, avoid all the disturbances around you, and at the end of the lecture it's very important to prepare your own short notes. Chalo. So with a very high positive energy, let's begin today's session. So with a numerical. So this question I gave it as a homework in the last session, right? So now let's try to solve this one. So 4 identical thin rods, each of mass m and length l, from a square frame. See here, there are 4 rods. So consider this is one rod, and then so one more rod, and then so one more rod, and then so one more rod. So like this there are 4 identical rods, so their length and mass are same, so they form the square. So now, so moment of inertia of this frame about an axis through the center of the square and perpendicular to its plane. So this square is made up of 4 identical rods, uniform rods. So now, so we have to find its moment of inertia about this point. So we have to find the moment of inertia about this point, which is passing through the square perpendicularly like this. So which is passing through the square. So now we already know that, so the moment of inertia about the center of mass for the each rod. So for example, I am taking so one rod. So consider this is a first one, second one, third one, and then fourth one. So the moment of inertia about the first rod, so we already know about its center of mass. So about its center of mass, it's going to be how much? So ml square by 12. So now it will be at a distance of, so this is forming the square, so this length will be l by 2, because one rod length is l. So from its center to here, its length will be l by 2. So now can we apply the parallel axis theorem here, because we need about this axis. We already know about this axis. So about this axis the moment of inertia is ml square by 12. And if I have to find here due to this rod, due to the first rod, what is the moment of inertia at the center? So how do we find? So these two are parallel, this line, see if I am drawing it straight means it's not straight, it's actually passing through this one like this into it. So here also you are finding into it. So these two will be parallel, so we can apply the parallel axis theorem. So then, so the moment of inertia, let me write the shortcut. So the moment of inertia at center of square due to rod 1, so the rod 1, so which will be equals to, so the moment of inertia due to rod 1 will be equals to, so its moment of inertia about its center of mass plus, so it is at a distance l by 2. So according to parallel axis theorem, so it's mass into l by 2 whole square, the distance square, right? About its center of mass, moment of inertia, plus m into, so the distance between them is l by 2 whole square. So from here, about its center of mass, we already know the moment of inertia, which is ml square by 12 plus, so this will be ml square by 4. So here it is going to be 12 is a LCM. So this is ml square by 12. So plus ml square plus this is 3 times. So 3 ml square, right? So which is nothing but 4 total 4 ml square by 12. So 4 ones are 4 threes are. So this is 4 ml square by 3. So this is moment of inertia due to one rod at the center of the square. So now we have to find due to all the 4 rods. So now due to this rod, again the same thing will get because through its center of mass. So the moment of inertia is ml square by 12, and again it will be at a distance of L by 2. Again you can apply the parallel axis theorem, you will get the same. And again you can apply the about the center of mass we know due to the third rod, and again this distance will be L by 2, right? So and again here also about its center of mass we know like this, and then we need about this axis. So again we can apply the parallel axis theorem here, L by 2. So this is due to one rod. So this is due to one rod. So the moment of inertia, the net moment of inertia will be due to all the 4 rods, I1 plus I2 plus I3 plus I4, right? So all these will be same because they are identical. So and that axis will be, so about which axis you are finding, it is parallel to all the center of masses, right? So that's why this is I2, I3 and I4 as well. So simply if you add all these, we'll get 4 into ml square by 3. Yes or no? So ml square by 3 plus ml square by 3 plus ml square by 3 plus ml square by 3, which is 4 ml square by 3. So the correct option will be 4 ml square by 3. Yeah, this one, option 4. 4 by 3 ml square is the correct option, guys. Clear? Simple question. So chalo, so let's move on to the next question. So what's the question says here? A thin rod of length L and mass m is bent at its midpoint into 2 halves so that the angle between them is 90 degrees. So now the moment of inertia of the bent rod about an axis passing through the bending point and perpendicular to the plane. So not plant. So this is plane. Plane defined by the 2 halves of the rod. See here. So first try to understand the given question. So there is a rod of length L and mass m. So this is of the rod length L and mass m. Length L and mass m. So now it is bent into 2 halves such that those 2 halves are perpendicular to each other. So now, so I can make those 2 halves. This is 1 half and then this is 1 more half. So it is like this. So 2 halves. So where the angle between them is 90 degrees. Okay. So now the moment of inertia of the bent rod about an axis passing through the bending point. So about an axis passing through bending point. Here it is the bending point. So and perpendicular to the plane. Let's suppose if it is lying on this plane, about this axis you have to find. About this axis you have to find. Now the simple thing. So shall I say that this will be of mass m by 2 and length L by 2. This also will be of mass m by 2 into L by 2 because this total is of mass m and length L. So now it is bent into 2 equal halves. So this one same mass and same length. So which are halved, m by 2 L by 2, m by 2 L by 2. So now about this axis I need the moment of inertia. About this axis I need the moment of inertia. So shall I find, so for this rod, so shall I find the moment of inertia here? And then for this rod also, shall I find the moment of inertia here? Here? Yes or no? So about this point we required. So from here, it will be at a distance of how much? This will be at a distance of, see, from about the center of mass we already know. About its center of mass we already know. Right? So what is about its center of mass? ml square by 12. So now this will be at the end, right? This will be at the end. So end means ml square by 3. For this rod, this will be the end. And for this rod, this will be the end. So we need the moment of inertia about end of the first rod and moment of inertia about the end of the second rod. So that is your axis. At this axis we required. So this point will act as end for the first rod and end for the second rod. Right. So that's why. So the net momentum will be, I can write. So the moment of inertia of end for the first rod first, then the moment of inertia for the end for the second rod. That's it. end for the first rod and end for the second rod. That's it. So now what we can write here? So this mass is m by 2 into, so what is the distance from here to here? From here to here, so we need, can we apply the parallel axis theorem? Or else, sorry, about the center of mass we know, at the edge, right, already it is at a length of L by 2 whole square by 3, ml square by 3, right? So I am writing ml square by 3 plus, because mass is m by 2, length is, this length is how much? L by 3. If it is of the rod of mass m and length L, so if you need the moment of inertia about its end, it should be ml square by 3. So now if the rod of the mass is mass of the rod is m and length is L, then it's a formula. Here mass is m by 2, so m by 2 I am writing, and length is L by 2, this total rod's length, so L by 2, so whole square by 3. So same for the second rod also, its mass also m by 2 into L by 2 whole square by 3. So from here I can write, so let me take this off. So I can write here, so this is going to be ml square by ml square by, so 4 into 2, 8 into 3, 24, plus here also ml square, because this is 2 square is 4, 4 into 2, 8, 8 into 3, 24. So which will be nothing but, so 2 ml square by 24, 2 ml square by 24, so which is ml square by 12. So are you guys able to understand this part? Again we are getting the ml square by 12, which is nothing but, so the moment of inertia of the rod about an axis which is passing through its center of mass, about the axis which is passing through its center. Yes or no? Ml square by 12. So that means in this particular case, so the rod is bent in such a way that this is of the rod, this is the rod, so which is bent in such a way that this rod is bent in such a way that, so whose mass and length were exactly halved. So here m by 2 and L by 2, and here also m by 2 and L by 2, and obviously this point will act as its center, so that here the moment of inertia about its center of mass is ml square by 12, and this point, this corner will act as a center, right, for this whole rod. If you again get it straight, so this point will act as a center, no? So then again it will be ml square by 12. So that point you should understand. Okay, so not only this way, so if you can bend it into like, so like this also, so if it is of mass m and then so at some angle, so 120 degrees, so then also if you make it straight, so this is of mass m by 2 and length L by 2, so this is of mass m by 2 and length L by 2, so if you make it straight, again this point will act as a center, so about it also the center of mass will be ml square by 12. If they ask you to find, so the center of mass about its bent point, so or else let's suppose if it is bent in this form, so like this, see the angle doesn't matter here. So clear? So this angle is 60 degrees. So this is m by 2 L by 2, and again this is m by 2 L by 2. So now if they ask you to find what is the moment of inertia about the bent point, so again if you get this straight, so then this point will act as a center, so this also will be ml square by 12. So in this case, in this case, and in this case, in all these cases the moment of inertia will be ml square by 12. So just you have to check that. So if you make the other part straight, so then that bent point is acting as a center of the original rod or not, so that you check it. So if it is same thing, so then the moment of inertia about the center or bent point will be same, ml square by 12. Okay, so in which cases it will not be equal, sir? So in the cases like if it is bent in the form of a circle, so let's suppose this is a rod, so this rod is of mass m and length L. So now if it is bent in this form, circular form like this, circular arc, if it is bent in this form, so then here if the center of mass, about its center of mass, the moment of inertia is ml square by 12. So but here it is not ml square by 12, so it will be something else. Clear guys? Understood? So these are the concepts that you should understand. This is a concept. Done? So let's move further. So now next, so the moment of find the moment of inertia of a uniform disk, so of mass m and radius r about an axis passing through the center of the disk and perpendicular to the plane of the disk. See here, so just imagine you have a disk here. So the disk means completely solid, guys. So this is a disk. Okay, so this is completely solid. Just try to understand. So that gym round plates will be there, na? In gym you can see, or else that solid ones, so which are of some mass and some width. So the solid ones, round circle ones will be there, na? So they are considered as a disk. Okay, so for the disk, so let's suppose this is a disk. I am holding the disk like this now. So now you are finding the moment of inertia about its axis, which is perpendicular to the disk. That means like this. If you are holding the disk like this, so about this axis we are finding the moment of inertia. If you are holding the disk like this, so then about this axis you are finding the moment of inertia, guys. About this axis. So this one, about this axis you are finding the moment of inertia. So generally in 2D I can represent that as this one. So this is a z axis. The z1 is a perpendicular axis. So the moment of inertia about z is equals to, so the mr square by 2. For the circular ring, see, this is for the disk. The same concept if it is for the circular ring. If I take it for the circular ring, so I'll write that also here. So this is a circular ring, so which is of radius r. So now if you are finding the moment of inertia about this point, again for the circular ring, this is a ring, not disk. What is the difference between ring and disk? This is just hollow, the ring. This one is so solid, completely solid. So here the moment of inertia about this z axis, so which we represent like this. So generally we represent like this. So this is the z axis. So which means the ring is in xy plane. This is the xy plane, let's suppose. So the ring is here and this will be the perpendicular axis. About this axis you are finding the moment of inertia. So which we already discussed, mr square. For the ring it is mr square about its center of mass, which is perpendicular to the plane of the disk, right? So and for the plane of the ring, so for the disk it's going to be mr square by 2. Clear, guys? Understand these statements. These formulas you should remember. Chalo. So next, so the moment of inertia of take the question, guys. So the moment of inertia of a circular disk of radius r and mass m and an axis passing from the edge of the disk and normal to the disk. See here. So here I am taking the disk. So this is disk. See here. So the moment of inertia of the uniform circular disk of radius r and mass m and an axis passing through the edge of the ring, edge of the disk and normal to the disk. Edge of the disk and normal to the disk. Let's suppose you are holding the disk like this. So now, so if it is the disk, I am holding the disk in my hand. So like this, this is a disk. So now this will be the axis which is passing through the center of the disk. Now, so we need here at the edge of the disk, so and tangential to the disk. See here. So passing from the edge of the disk and normal to the disk. So this is the, see, this is the disk. So you know about its center here. You know about its center. So now we need at this point, which is passing, just passing through the edge of the disk and which is perpendicular to the plane of the disk. So about this point we required. So what is that point? So I can say that I can represent it in 2D as like this. So this is the perpendicular one, and now I need about edge here. So if we have to imagine it in 3D, so how do we imagine this one? So about this point and here, these two lines indicates, so this one is about its center, and then this here we are finding. So can we apply the parallel axis theorem here? So this length will be the radius of the disk. So now, so I need, let's suppose this is some x dash axis. So the moment of inertia about x dash axis will be equals to, so the moment of inertia about its center of mass plus the moment, the distance is mass into the distance is r whole square. Here I am applying the parallel axis theorem. let's apply the parallel axis theorem. So then next, so we have Ixx dash is equals to, so what is the moment of inertia about its center of mass? So for the disk, just now we have seen, so which is mr square by 2, right, plus, so this is mr square, so which is nothing but total 3 by 2 mr square. That's it. So the questions will be easy, just you have to you should not commit the calculation mistakes. That's it. Understood guys, this part clear? Chalo. So let's move for the next question. So see this question. So what's the question says? The moment of inertia of a uniform circular disk of radius r and mass m about an axis touching the disk at its diameter and normal to the disk. Again same question. So try to understand this. So this is a disk. Consider this is a disk. So now the moment of inertia of the uniform circular disk of radius r, so this disk is of radius r and mass m about an axis touching the disk at its diameter. So see here, if I consider this is the diameter, so this will be the diameter. So then touching the diameter and normal to the disk. So touching the diameter and normal to the disk. So we already know about its center of mass for the disk mr square by 2. So now we need here. So can we apply between these two axes we need. So which is nothing but can we apply the parallel axis theorem? Same as the previous one. So if I represent it in the 2D, so I can write here like, so I know about this axis. Now they are asking me about an axis here. Yes or no? This line indicates if I am drawing it on the board, so which means it is into the plane. Okay. So if I am drawing here, so it means here it is into the plane like this. So I can't represent into the plane on the board. So that's why I am drawing the z axis like this. This will be x axis, this will be y axis, and this will be z axis. Okay. So remember that. Clear guys? So this is x, y, and then z axis. Clear? Chalo. So I can apply the parallel axis theorem here. Here let's apply the parallel axis theorem. So what do we get? Same answer. So the about this axis we required, which is touching the diameter. So touching the diameter and perpendicular normal to the disk like this. So about xx dash is equals to, so the moment of inertia about its center of mass, plus, so it will be at a distance how much? So r distance. So plus mr square. So this is we already know mr square by 2 plus mr square. So which is nothing but again 3 by 2 mr square. This is 3 by 2 mr square. Clear guys? Understood? Chalo. So let me get some water. Clear? Hope you guys are able to understand the concept. So now the perpendicular axis theorem. See, the perpendicular axis theorem is applicable for only 2D bodies. Only 2D bodies. Which means for the laminar sheets. 2D laminar sheets. Okay. So whereas parallel axis theorem is applicable for 1D, 2D as well as 3D. Okay guys, chalo. So now if I take any body, so let's suppose some rigid body, so which is in xy plane. Now I already know the moment of inertia about, so the x dash axis and y dash axis. Now I would like to find the moment of inertia about, so the z dash axis. So the moment of inertia about z dash will be equals to, so the moment of inertia about xx dash plus the moment of inertia about y dash. That's it. Not only in the z dash. So if the body is in the, let's suppose, so consider, let me take the formula. If the object is in, so the yz plane. Sorry. So if the object is in yz plane, so then the moment of inertia about xx dash will be equals to, so the moment of inertia about y dash plus the moment of inertia about z dash. Or let's suppose if the object is there in the xz plane, so then the moment of inertia about y dash will be equals to, so the moment of inertia about xx dash plus the moment of inertia about zz dash. That's it. So that means if you already know the moment of inertia about any two perpendicular axis, and if you have to find the moment of inertia about another third particular axis, third axis, so then you can apply the perpendicular axis theorem. So the third axis moment of inertia will be equals to, so the other two moment of inertias adding. Okay, clear guys? Simply, so this is the concept. Done? Chal. So now let's apply the moment of inertia for this question. So this is the ring. This is the ring. So this is, let's suppose this is the x plane. So this is the y plane, right? So now I need to find the moment of inertia about, consider this point. Let's suppose I need to find the moment of inertia about this point. So if I draw the line like this means, so it will be here like this. It is into the plane like this. About this axis we need to find. Already two perpendicular axes are there. This is one axis in the plane. This is one other axis in the plane. So this is not in the plane. See, just imagine this is the plane. So the x is in the plane and y is in the plane. So but the z is not in the plane. It is into. It is into, right? Into the plane. So I can find, so the moment of inertia about this z axis will be equals to, so the moment of inertia about x plus the moment of inertia about y, right? So as it is following the symmetry, see x and y, so the moment of inertia about x is equals to I, the moment of inertia about y is equals to I, because it is following the symmetry, yes or no? So this one or this one about the moment of inertia, it will be same, right? So I am taking the moment of inertia about x is equals to moment of inertia about y is equals to I. So the moment of inertia about this one I plus I. So about x is I, about y is also I. So which is nothing but, so the moment of inertia about z axis is equals to 2I. So from here, what is the moment of inertia about z axis for the circular ring? We already know. So which is nothing but mr square. Which is nothing but mr square, the moment of inertia for the circular ring about its z axis. Circular ring about its z axis. So which is mr square. So which is equals to 2 times I. So from here, so the moment of inertia about x axis or y axis, so is mr square by 2. So that means you just remember now. So the moment of inertia for the circular ring about its z axis, so about its perpendicular axis is going to be, or else about its z axis, right? Better. Let's write z axis. So which is mr square for the circular ring. So now the moment of inertia about its diametrical axis. So we can say this is the moment of inertia about its diameter, and this is also the moment of inertia about its diameter. So the moment of inertia about the diameter of circular ring is equals to mr square by 2. Yes or no? So this I is nothing but what is this? So the moment of inertia about x axis and the moment of inertia about y axis. So these are all formulas. I'll give it in the tabular column at the end. So while summarizing, you'll understand better, because all these formulas you have to remember. So we can't go for the derivations in the questions every time. Clear guys? Done? So this you remember, this part. This is for the circular ring. Just simply write ring which is of mass m and radius r. Chalo. So let's go for the next one. So for the disk, so this is the disk now. This is the disk. So now if I have to find moment of inertia about this particular z axis I required. So this z axis means like this here about this axis. So this is the moment of inertia about x and this is the moment of inertia about y, right? So now the moment of inertia about x will be equals to the moment of inertia about y, which is equals to I, because it is following the symmetry. This is diameter and this is also diameter. For the circular disk, if you take the uniform disk, So then about this axis or about this axis, both are diameters only, right? So the moment of inertia about this, whatever you get, so the moment of inertia about this also you'll get the same, because either side same mass, same length, same dimensions here. So here either side same mass, same dimensions. Here also same thing. If you cut this also same mass, same dimension, so that the moment of inertia also will be same, because it's a symmetry. Same here also, the same thing I wrote about this x-axis or y-axis, which means diametrical axis. So the moment of inertia will be same. So you can write the point here also, it's symmetry. It is symmetry, right? So now next, so I can write here the moment of inertia about z-axis we need. So the moment of inertia according to the perpendicular axis theorem. So the moment of inertia about x, y we know, let's say. So then the moment of inertia about another perpendicular axis we required. So 3 perpendicular axes are there. So I can apply the perpendicular axis theorem. So the moment of inertia about z is equals to, so moment of inertia about x plus moment of inertia about y, simply, right? So from here the moment of inertia about z, so which is equals to, so let this be I, so I plus I 2I. So for the circular disc we already know what is the moment of inertia about the z axis. What is that? For the circular disc, mr square by 2. For the circular disc the moment of inertia about its center or z axis, perpendicular axis, is mr square by 2, so which is equals to 2 into I. From here I can write I is equals to mr square by 4, mr square by 4. So the moment of inertia about, so the x and y, which we also call it as about the diametrical axis for the circular disc. So now you can write the conclusion here. So about its z axis it's going to be mr square by 2. About its diametrical axis it's going to be mr square by 4. Diametrical axis, so it's going to be mr square by 4. So for what? For circular disc. This is for the disc. This is for the circular disc. Clear? Understood, guys? So these are the standard results everyone should remember. Done? This one and this one. Chalo. So let's see one question. So what's the question says here? The moment of inertia of a disk of mass m and radius about an axis, so which is tangential to the circumference of the disk and parallel to its diameter is. See here, try to understand the question. First, there is a disk. So here is a disk. So now, so the moment of inertia of a disk of mass m and radius r about an axis which is tangential to the circumference of the disk and parallel to its diameter. See, consider this is the diameter. Consider this is a diameter. So now what they are saying, tangential to the circumference of the disk and parallel to its diameter. Let's say, or otherwise take this point. So consider this will be better. This is the diameter. So now I need tangential and parallel to its diameter. Tangential, see here, tangential to the circumference. This is the circumference. Tangential to the circumference and parallel to the diameter. Parallel to the diameter. So I know about its diametric axis already. I know about its diametric axis. Now I need it here. So this distance will be r. Can I apply the parallel axis theorem here? About this axis for the disk I know. This is a disk. Yes or no? If it is a disk, about this axis I know. About this axis means diametrical axis. What is the diametrical axis moment of inertia for the disk? mr square by 4. Right? So now I need parallel to the diametrical axis here at a distance r. Right? So I can apply the parallel axis theorem. So I can apply the parallel axis theorem. So the moment of inertia about, let's say this point is xx dash. So the moment of inertia about xx dash is equals to, so the moment of inertia about its diameter for the circular disc plus, so mass is m and the distance, at what distance we required? R. So m r square. Right? So from here about its diametrical axis mr square by 4 plus, so this is mr square. So which is nothing but 5 by 4 mr square, which is nothing but 5 by 4 mr square. Option 1 is the correct answer. Clear, guys? Understand the question properly. About an axis which is tangential to the circumference of the disk, tangential to the circumference of the disk, and parallel to its diameter, parallel to its diameter. So I am considering this diameter, or else you can, if you consider this diameter, about this point you have to calculate. If you consider this as a diameter, about this point or this point you have to calculate. That's it. Okay, chalo. So let's take the next question. So the question number 7. What's the question says here? So moment of inertia of a uniform circular disk about the diameter is I. So if I take this is the disk. So about its diameter is I. So let's suppose about its diameter I. So what is this formula? We already know, mr square by 4 about its diameter. Now, so it's a moment of inertia about an axis perpendicular to its plane and passing through a point on its rim. See here. So next case, so this is a disk again. So let's say, so its moment of inertia about an axis perpendicular to its plane and passing through a point on its rim. So passing through a point on its rim, and then so here, so that means already, see, perpendicular means, shall I take like this? About its perpendicular axis we already know. About its perpendicular axis we already know. Now we need at a point, we need at a point, so which is parallel, see here, we need at a point, so about an axis perpendicular to its plane and passing through a point on its rim. So passing through a point on its rim, you just imagine it like, so through center we know this, this line indicates this one here like this. So and then we need here, so here we need, so let the moment of inertia, here it is I dash. So then what we can write, this distance will be r, right? So then I can write the moment of inertia about its center perpendicular axis is what? So I about its center of mass, or else you can write I about z plus, so we need this one x dash, right? So plus mr square, right? So what is this one? Iz for the disk about its center perpendicular to plane of the disk, so which is mr square by 2, right? Plus mr square, so which is nothing but 3 by 2 mr square. So actually we need this in terms of this one. We need this because in terms of options they are gave 3i, 5i, 6i, 7i like that. So what I am doing is, let's divide. So I dash by I. Let it be equation number 1 because I need this in terms of this. So that's why I drew separate diagrams. About its diametrical axis we already know. So they gave it as I, that I is mr square by 4. Now about a point, so which is touching its rim and parallel to its center like this. So there we are finding using the parallel axis theorem. So which I got it as m by 2 mr 3 by 2 mr square. So now I need this in terms of this. So I'm just dividing these two equations. So which is mr square by I dash is what? 3 by 2 mr square by, so mr square by 4. Mr square by 4. So mr square cancel. So I dash by I is equals to, this 4 goes up, 12 by 2. So 6. I dash by I is equals to 6. So therefore I dash is equals to 6i. So the I dash is equals to 6i. Option 3 is the correct one. Clear, guys? Understood the concept? Chalo. So now let's move further. Done? Chalo. So now let's see the moment of inertia of some standard bodies. So whatever the formulas that I am going to give now, so these all formulas you have to remember. So already we have derived some formulas, that means we already discussed about some formulas. So some formulas will be new to you from now. So what are the very important ones, from it also I'll tell. Okay. So this is a uniform rod about its center of mass. So about its center of mass we already know. So this uniform rod is of mass m and length l. So about its center of mass ml square by 12, and about its one end, either this side or this side, so it will be ml square by 3. This is ml square by 12, this is ml square by 3. So you should get these formulas now itself, guys. Okay, so this is ml square by 12 and this is ml square by 3. So that's fine. So now let's come for the ring. This I am taking it as ring. For the ring, about an axis perpendicular to the ring. Ring is here. Let's suppose the ring is there on this board. So now if I need it on the center, so which is passing through its center, perpendicular to its center and passing from the center, right? So I about the z axis. That z axis I am representing like this. This is the z axis. See, x, y. So if I draw a line this one, this means it is a z axis. So that means about this axis you are finding. This is the ring. About this axis, what is the moment of inertia? mr square for the ring. So now, if we need about the diametrical axis, if it is the ring, about this axis or this axis, which is in the plane, the diameter which will be in the plane. So which means mr square by 2 for the ring. This is also the ring of mass m and the radius r. Okay. So about its diameter here or here. So which will be mr square by 2. So about its perpendicular axis, it's mr square. About its perpendicular axis, mr square. About its diameter, like this or like this. So it is mr square by 2. Same for the disc also. About its diametrical axis, about its z axis, perpendicular axis. This is the disc, and which is about this axis, which is passing through the disc and perpendicular to the disc or plane of the disc. So about this axis, so that I can represent it in 2D as this one. This means the z axis, like this, into it. So about this axis you are finding. So which is nothing but mr square by 2. So now if you need about diametrical axis, either this or this, which are in the plane, either this or this, which are in the plane, which is mr square by 4. So there it is mr square about its perpendicular axis, and about its diametrical axis mr square by 2. Here about its perpendicular axis or z axis mr square by 2, and about its diametrical axis mr square by 4. So this is the difference between the ring and the disc. Okay. So if you remember the ring and disc, so then you can remember hollow cylinder and solid cylinder easily. Okay. So the moment of inertia about hollow cylinder and solid cylinder, same formulas. Hollow cylinder same as of the ring. So solid cylinder same as of the disc. Clear? So those formulas also we'll see. So these 6 are clear. First, about a rod, about its center and about its end. So ring about its perpendicular axis, z axis, and about its diametrical axis. And for the disc, about its perpendicular axis, which is z axis, and about its diametrical axis. Now, so let's go for the shell. So which is of spherical shell. So one is of radius r1, the other one is of radius r2. So then the moment of inertia about its perpendicular axis will be, so m into r1 square plus r2 square by 2. M into r1 square plus r2 square by 2. So now this is called the 8th one, the rectangular lamina. This is a rectangular lamina. So which is of so length L and breadth B. So length L and breadth B. So then the moment of inertia about its x dash is equals to, so half of its mb square by 12. About its x dash means mb square by 12. So about its y dash axis, so ml square by 12. So y dash ml square by 12. So x dash about this axis, so mb square by 12. So this also you should remember. This is a rectangular lamina, right? So then for the same rectangular lamina, if you need about its z axis, this is a perpendicular axis. This indicates about its z axis like this. So which is passing through the rectangular lamina, perpendicular to the rectangular lamina about this axis. So which will be equals to, so the moment of inertia, this, see, about this axis means we already know about it, about its diametrical axis. About this axis we know, about this axis we know. So now can we find about this axis according to the perpendicular axis theorem? According to perpendicular axis theorem, so we can say that the moment of inertia about z axis means into the plane. So we already know about this plane and we already know about this plane. Yes or no? We already know about this axis and we already know about this axis. So which is mb about this axis mb square by 12, about this axis ml square by 12. Now I need about this axis, about this axis. So here all three planes are mutually perpendicular. You can apply the perpendicular axis theorem. So the moment of inertia about z axis is equals to moment of inertia about x axis plus moment of inertia about y axis, right? So about x axis mb square by 12, about y axis ml square by 12, already we have seen here. About x axis this one mb square by 12, about y axis ml square by 12. So if we add these two, so we'll get about its z axis, perpendicular axis. So now if you need about its diagonal, diagonal is different. So if it is the rectangular lamina, so this is the diagonal axis. Don't think these two are same. This indicates, the above one indicates this plane. So this one is a diagonal. So if it is a rectangular lamina, if it is a rectangular lamina, about this axis you are finding, about this axis. So this is the diagonal. So which is m l square b square by 6 into l square plus b square. M l square b square by 6 into l square plus b square. Very less chances are there to ask. Okay, chalo. So now if you need about, so the triangular lamina, this is the triangular lamina. So for the, which is of height h, if you need the moment of inertia about its base, so then, so its height is h, so m h square by 6. Its total moment of inertia about its base will be, so m h square by 6. Now, so this is a square which is of mass m and side a. So each side is a. This side a and this side a, and then this side is also a. All the sides a. So then the moment of inertia about, so its x-axis, x-axis means this one. The moment of inertia about its x-axis is m a square by 12, and moment of inertia about its y-axis m a square by 12. Again it's a, right? So m a square by 12. Sorry, here all sides are a. So about its y-axis m a square by 12, about its x-axis m a square by 12. So if you need about its z-axis, if you need about its z-axis, so you can apply the perpendicular axis theorem. According to perpendicular axis theorem, about its z-axis, so which will be equals to about its x-axis plus about its y-axis. So about x-axis m a square by 12, and about y-axis m a square by 12. So which is nothing but 2ma square by 12. So which is nothing but ma square by 6. Which is nothing but ma square by 6. The moment of inertia about z-axis. And if you need the moment of inertia about diagonal axis, again same thing, because its side is a. So ma square by 12. Clear guys? About its diametrical axis, sorry, diagonal, again ma square by 12. So only about z-axis it is ma square by 6. About x-axis, y-axis and diagonal it's going to be same for the square. And this is a hollow sphere. So very important, everyone should remember guys. So for hollow sphere it's 2 by 3 mr square. About all the axis, x-axis or y-axis or z-axis, it's going to be 2 by 3 mr square. And for the solid sphere, about all the three axes it is 2 by 5 mr square. So hollow sphere 2 by 3 mr square and solid sphere 2 by 5 mr square. You should remember. So the questions based on these are very important. Okay, mr 2 by 3 mr square and here 2 by 5 mr square. Hollow 2 by 3 and solid 2 by 5. Remember it like that. Okay, then so cone. So this is a hollow cone, the first one, and this one is a solid cone. This is hollow cone, this one is a solid cone. So for the hollow cone, about its y dash axis, this is a y dash axis. So then mr square by 12, so mr square by 2, sorry. So here about its solid y dash axis for the solid cone, m by 10 mr square. Here mr square by 2, here it is m by 10, 3 by 10 mr square. Clear? Chal. So now for the hollow cylinder same ring. Hollow cylinder same ring. About its axis mr square. So about its horizontal axis like this, perpendicular axis, sorry, about its perpendicular axis, if the cylinder is like this, about its perpendicular axis, so it's mr square by 2 plus ml square by 12. Mr square by 2 plus ml square by 12. So but for the cylinder, about its axis generally mr square, so which is same as of the ring. So if it is a solid cylinder, same as of the disc, same as of disc, mr square by 2, mr square by 2 about its axis. So now about its perpendicular axis, mr square by 4 plus ml square by 12. So here also mr square by 2 plus ml square by 12. So here mr square by 4 plus ml square by 12 for the solid cylinder about this axis, about the perpendicular axis. Clear? Understood guys? This is also solid cylinder. So these formulas everyone should remember. All these 20 moment of inertias of different bodies, especially so the hollow sphere and solid sphere, and hollow cylinder and solid cylinder. Okay, and then rod and ring and disc. So these are very important mainly. So then rectangular lamina, a triangular lamina, so square. So all these you have to remember. Okay, chalo. So chalo, so take this question guys. Can you guys take this as the homework? Find the moment of inertia of a solid sphere about a tangent to the sphere where mass of the sphere is m and radius is r. So they are saying solid sphere. So this is the sphere. First thing is, so for the solid sphere, what is the moment of inertia about its center, about its z axis, about its perpendicular axis? This is a solid sphere. So 2 by 5 mr square, 2 by 5 mr square. So just now we have seen, where is that? Yeah, so 2 by 5 mr square. So whereas for the hollow sphere, 2 by 3 mr square. So here they are saying clearly solid sphere, so about its center. So then where mass of the sphere is m and radius is r, where do we need? About a tangent to the sphere, about tangent to the sphere. This is the tangent to the sphere. So can we apply about this axis? We already know. So we need here about tangent. So which means about this axis we know. Now we need about this axis, tangent, like this. So which is parallel to this one. So obviously, can we apply the parallel axis theorem? We can apply, so the parallel axis theorem. So we need about, so this is x dash, about the tangent. So about x dash is equals to the moment of inertia of center of mass plus, so this distance will be the radius of the sphere, obviously. So the m into r square. So this is 2 by 5 mr square for the solid sphere plus mr square. So if I take 5 as the LCM, so this is 2 mr square plus this is 5 mr square. So which is nothing but 7 mr square by 5, or else 7 by 5 mr square. 7 by 5 mr square. Option 2 is the correct one. Done guys? Clear? Chalo. So the 9th question. So what's the question says? The mass of the cylinder is 10 kg and radius is 10 meter. So find the moment of inertia of the solid cylinder about a tangent to the cylinder. See here, solid cylinder. So if I take, this is a cylinder, solid cylinder, about its axis we already know. For the solid cylinder, about its axis, for the solid cylinder, about its axis will be same as of the disc. So which is mr square by 2, about its axis. So now I need about a tangent to the cylinder, about a tangent to the cylinder. So this distance will be of radius. So you can apply the parallel axis theorem here. Can we apply the parallel axis theorem here? Yes or no? So simply we get, so the moment of inertia about this axis, x dash axis, is equals to, so the moment of inertia about its axis plus, so its mass is m and the distance is r, so r square. So this is mr square by 2 already we know for the cylinder, solid cylinder. So plus this is mr square, right? So which is 3 by 2 mr square. So but here the values are given, I guess. Yeah, so substitute the values. 3 by 2 into, so what is mass? 10 kg into what is radius? 10 meters. So 10 into 10, r square means. So 2 ones are 2, 5s are. So 15, 150, 1500. So 1500 kg meter square. So moment of inertia units are kg meter square, right? So 1500 kg meter square. Option 2 is the correct one. Clear, guys? So 3 identical spherical shells. So spherical shells means what we should consider? Spherical shell means hollow sphere. This indicates the hollow sphere. Okay. So each of mass m and radius r placed as shown in the figure. Okay, fine. So then consider an axis xx dash which is touching the two shells. This is a xx dash axis which is touching the two shells and passing through diameter of the shell. Passing through diameter of the shell. So see here, passing through diameter of the shell. So now moment of inertia of the system consisting of these 3 spherical shells is simple. So for the, let's consider this is the A, this is B, this is C. So the moment of inertia about A we already know. So passing about the diameter of the spherical shell. So which is nothing but 2 by 3 mr square about A. About A. So now, so the moment of inertia about B will be, so about diameter we know. So now we need about tangent. So which is nothing but 2 by 3 mr square plus mr square, yes or no? Simple thing. This axis is for this B1, for the B1, this axis is a tangent, right? It is a tangent. So now about its diametric axis we already know. About its diametrical axis we already know. What is that? 2 by 3 mr square for the spherical shell. So plus parallel axis theorem I am applying. So its mass is m. So this distance will be r. So that's why 2 by 3 mr square, 2 by 3 mr square plus mr square. So which is 5 by 3 mr square. Right? So then the moment of inertia about C. This is a C1. So whose radius is r. Right? So for this also it is acting as a tangent. So now again for this also about its diametrical axis we already know. So what is that? 2 by 3 mr square plus, so this is mr square. So which is nothing but 5 by 3 mr square. Right? So then the net moment of inertia what it will be? So the I net, the total moment of inertia due to all these will be, so the moment of inertia due to A plus B plus C. So which is nothing but, so 2 by 3 mr square plus 5 by 3 mr square plus 5 by 3 mr square. So all here are 3 LCM. So that we get 2 plus 5, 7, 7 plus 5, 12. So 12 mr square. So which is nothing but, so 4. So the total is 4 mr square. So 4 mr square. Option 4 is the correct one. Clear, guys? Understood this part, everyone? So just it is passing through the first one. That's why I am directly taking the spherical shell. They said it's hollow sphere. So passing through its diametrical axis, passing through diameter of the shell. So about its diameter for the hollow shell. This one, where is that? For the hollow sphere, so which we already know, 2 by 3, see, about this axis, about this diametrical axis, 2 by 3 mr square. So for the first sphere, it is passing through its diameter. So that's why 2 by 3 mr square. For the second sphere, it is passing through its tangent. So then can we apply the parallel axis theorem here? So about its diameter, we already know, 2 by 3 mr square, plus here we required. So that's why plus mr square. At a distance r, so that mr square, right? So for the third one also, for the C1 also, it is same thing because at the tangent. So for the about the diameter 2 by 3 mr square plus here we required, so plus mr square. Done. So total, so IA, IB, IC we got. So the net will be IA plus IB plus IC. So the final answer we got it as 4 mr square. Clear? So as I said previously, so basically we have to take, so the solid cylinder, hollow cylinder formula, and hollow sphere, solid sphere, and these formulas. So the ring, disc, so and rod, these formulas are very important, the moment of inertia. So everyone should remember these guys. Okay, done? Clear? So that's it from my end for today's session. So in the next class we'll solve more questions about the moment of inertia of different bodies, and we'll also discuss about the radius of gyration. Okay, so till then, keep studying. All the very best. Bye guys.